relative maxes and mins are, and believe it or not, the second derivative test does too. They both tell you the same thing. The first derivative test does it by saying, okay, it switched from increasing and decreasing. Okay. The second derivative test tells you there's relative maxes and mins by telling you, oh, it's concave up or concave down. So there's different ways of doing it. Now, a lot of people are like, well, it seems silly to do the second derivative test because on the way to the second derivative, you would have already done the first derivative. So why not just do the first derivative test? And that's pretty accurate. A lot of people, for that reason, would just rather do the first derivative test and be done with it. The reason that we have to learn the second derivative test and practice it is because we basically have to be able to do those problems where they specifically set them up for us to only have enough information to do the second derivative test. Does that make sense? Okay. Now, the second derivative test is different from just the plain old second derivative where they're saying find the concavity and all that. Okay, the second derivative test is talking specifically about using the second derivative to find the relative maxes and relative mins. Okay, the first derivative test, the second derivative test, they're all about finding relative maxes and relative mins. That's the only thing those tests are doing. The rest of it, the finding the relative maxes, finding relative mins, finding increasing, finding decreasing, finding concave up, finding concave down, finding all that stuff, that is just using your derivatives to find information. Does that make sense? That is not the first derivative test and second derivative test. Those specific tests are only for finding your relative extrema. That's what those specific test titles are for. Those test titles don't seem to come up. They don't seem to say, therefore, by the first derivative test, I found this. I have not seen them require that on an FRQ, to be honest. I've seen these types of questions show up for the most part as multiple choice questions, which means that they can manipulate the question to force you into a specific path, which is why we have to practice both of them. Does that make sense? They can force you down one direction where you just have to do what they choose. All right. So let's go ahead and look at the information here. I think there was a sheet I was going to print out for you today that kind of related all three of these together, but I'll look for that in a second. So it says that you are given the first derivative, and we want to find the points of inflection. And basically, when we find the points of inflection, what are we kind of finding? This is not the name of it, but it's kind of what we're basically doing. It's kind of the critical points, but that's not actually what they're called. They don't have a name, but it's kind of the critical points of the derivative graph. So we're basically looking, when we're looking for the points of inflection, we're looking for where f double prime equals 0. Okay? So where on the graph, if this is the first derivative, where would the second derivative equal 0? At 0, -1. Okay, right there. That's a slope of 0. -2. And then at 2. So that's where your points of inflection are, okay? Those are all, we're saying the second derivative equals 0. So these are all where you have a horizontal tangent, where the first derivative has a horizontal tangent. Because they said this is not the graph of f, this is the graph of f prime. So we're not looking at the original function, we're looking at the derivative function graphed. Okay. So now they want us to say the intervals of concavity, so I'm going to go ahead and do my sign chart. I guess I always draw those as straight lines like they're ending, but they're not. So we got negative infinity and positive infinity. We got 0, we got -2, we've got +2. So between negative infinity and negative 2, our second derivative, so we're thinking of our second derivative, our first derivative has a positive output, right? Our first derivative has a positive output, but we're not thinking about our first derivative here because they are asking about concavity, so we're not thinking about our first derivative. We're thinking about our second derivative. So our second derivative is talking about what type of slope we have. So I'm not thinking about the fact that my first derivative has a positive output. I'm thinking about the fact that this has a negative slope right here. Does that make sense? Okay, so I'm going to say negative sign, negative slope. Okay, so right here, I'm going to say, just for understanding what I'm doing here, I'm going to say the second derivative right there is less than 0. Because my graph is not of my second derivative, my graph is actually of my first derivative. Does that make sense? My graph is of my... So from negative infinity all the way to negative 2, that's my second derivative is a negative slope. Okay. From negative 2 to 0, what slope do I have? Positive slope. From 0 to 2, what slope do I have? Positive slope. Okay. And then from 2 to infinity, what slope do I have? Negative slope. Okay. Does that make sense? We're okay? So if we were to describe where the graph is concave down for the original function, if we were to say where the original function is concave down, what would we say? Negative infinity to negative 2 and 2 to infinity, okay? And it's concave up, negative 2 to 0, and 0 to 2. And I'd have to double check, I need to double check some of my old answer key. Let me double check this answer key actually, because I just took it out, and see if they would skip the 0 like that, or if they'd go straight from negative 2 to 2. They would go from negative 2 to 2. Over that 0. It's a great question. It's an issue of including I have to think about this. I have to think about what the graph would look like. A point of inflection is where the graph switches concavity. And if you are concave up and then you're still concave up, you are not switching concavity, which means that that is not actually a point of inflection. So it should be this. It should not split at 0. It's a point where you have a horizontal tangent, but it's not actually a critical point. Or it's not actually a it's not actually a point of inflection, basically. Kind of like how we have our critical points where they could be relative maxes or mins, but sometimes they're not. This is one where you find it as a critical point, but it's not actually a point of inflection. So we locate it as something that could be important, and then when we do our sign chart, we find out, oh, it's not a point of inflection. It's where a horizontal tangent occurs, but it's not a point of inflection. Does that make sense? Okay. So the idea of a critical point, but technically you don't call them critical points because they don't have names for the second derivative. Okay. Yeah, you can see it in the original function because you'll be able to see, like, in an original function graph, you'd like look at this, something like that, and you'd say, oh, this is concave down, and this is concave up, and you'd say, oh, the point of inflection is where it switches. It's switching from concave down to concave up, so the point of inflection is approximately right there. And you'd be able to say the second derivative is going to be negative right here, the second derivative would be positive right there, and the second derivative would be 0 right in here. Does that make sense? Yeah. 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 But it's a fluency thing, right? So it's going to take a little bit for us to make those connections, and it's not something we make those connections about in one day. I think it takes some time for it to sink in because we're talking about a vocabulary mixing with pictures, and I think that just takes some time. So we are, later on in this unit, we do start to connect this vocabulary with pictures of graphs, and we do connect F with F prime with F double prime. So it's not just a one-day thing. Yeah. And we are going to, some of the other days, if you look ahead of what we're studying, we are going to spend some days where we find this information, and then we use this information to sketch graphs, which is really interesting. It's the part of this that where I really like this graph, because you can do it all by hand. You can take an equation, you can find all this stuff, and then you can sketch the graphs by hand, which I think is really cool. That's the part of this unit that like blew my mind, was that you could find all this stuff without a calculator. Yeah. Uh-huh. Which part?
Like it's like in the first part where you have like draw the little stuff, and then like our notes say that concave up and concave down next to the point, but I just don't know if I like wrote them wrong or just don't understand.
Oh, because we're talking about this is the graph of the first derivative. And what we were talking about in the notes probably, because this doesn't look concave up and concave down because it's not the graph of the function. So if we were to use this information to sketch the function, it would actually look concave up or concave down. So this is just saying, since it's slanted down, the original function would be concave down for that portion. Since it's slanted up, the original function would be concave up for that portion. But we are interpreting the second derivative. We're not actually saying what the original function looks like. That's why this appears to be concave down and that appears to be concave up, because we're not actually looking at the original function. So the concavity that you're seeing here does not match what we expect. Does that make sense? Yeah. Okay. So we're just saying negative slant means that the original function is going to be concave down, but we don't even see the original function. We don't know what it looks like. We just know that right there it's going to be concave down. Does that make sense? Okay. Perfect. All right. How do you guys feel about looking at these types of graphs? So here, what they basically have done is they've given you a sign chart, and they're asking you to use the sign chart to interpret and give the relative extrema, give the concavity, give the location of the points of inflection. So shall we go through and find what we can? Okay. So here it gives us, this is the first derivative, this is the second derivative. So for the same, it's a twice differentiable function. What they're telling you is they're telling you that it's a function that's continuous, that you can differentiate twice. So they're just saying that it's fair to do this process on it. So if this is our first derivative, now I'm not used to seeing a sign chart looking like this. So if you want to put it into our normal sign charts, we could. We could say 1, negative 2. And then we could say positive, negative, negative, and then it looks a little bit more comfortable to us. Doesn't that already feel better? As soon as I write it the way I'm used to seeing it, I already feel better. Okay, so this is my first derivative. So what do I see about my first derivative? Relative min at x equals negative 2, okay, and then what else do I see? Relative max at x equals 1, okay. So the work that we just did, the relative min, the relative max, we were using the first derivative test to find this. Our increasing interval is what? -2 to 1, okay. Our decreasing interval is and 1 to 3. Okay. Now, I've talked to a few individual people about this. The person who did my AP training is also someone who does a lot of AP grading, and she told me that it used to be, from what I've heard, it used to be that you kind of always use parentheses on increasing and decreasing intervals, which is how I learned it, which is how I've taught it, and that there have been more specific definitions that have kind of come out where you can put brackets. But she said that when they grade FRQs, if you always put parentheses, you will always get the points. So the way that I've taught you in the past, if you put parentheses, and this is if you compare our answers against answer keys for FRQs, you'll see brackets in there. You'll see students getting points for brackets. But she said if I keep teaching my students with the parentheses, they will always get the points. So if you want to always do parentheses, that's fine. You'll be safe. Yes? -3, -2 for this one. Oh, -2. Sorry. Thank you. So for this one, we could do the 3s in parentheses because that's how I've taught my students in the past. We could also do brackets because that's how they gave us the interval, and they gave us that the interval was negative. So I'm going to keep doing parentheses because that's how I've always taught it, but just know that you are safe to put parentheses and you'll still get full points. That's something I specifically asked on because it's been messing with my brain. All right, our second derivative. I'm going to go ahead and do this part, and actually I should have stopped it because it did stop at 3. Okay, so over here we got -3, we got +3, we got our second derivative, has a, kind of critical value sort of thing at -1/2, not at 0. It is 0 at -1/2. So now if we were using the second derivative test, we would say that -2 is a number that falls in between -3 and -1/2. We would say that -2 falls in between those, that this is positive, therefore it's concave up. And we would say that that confirms that -2 is a relative minimum. Does that make sense? That's how the second derivative test works. Just because it's a critical point for the first derivative, and it falls in this interval, and since this interval is concave up, then that critical point must be a relative minimum. So not any point on that interval has to be a relative minimum, but any critical point on that interval has to be a relative minimum. And you get that from the first derivative. So critical points from the first derivative that are concave up have to be relative minimums. That's what the second derivative test says. Does that make sense? And then over here, 1 was a critical point according to the first derivative. 1 is on the interval from -1 to 3. 1 is on an interval that is concave down. Therefore, 1 is a relative maximum. So what we just did is we just used the second derivative test to confirm that our relative min and our relative max are right, that we use the first derivative test, and then we use the second test to confirm that our conclusions from the first derivative test were correct. Does that make sense? So that's how the second derivative test works. Okay? Yeah, the second derivative test is really redundant of the first derivative test, because the second derivative test, remember, the second derivative test is all about relative mins and relative maxes. Finding the second derivative itself is about concavity and points of inflection. But when I say second derivative test, when I say that word test on the end, I'm talking about relative mins and maxes. which I already found. Which is why people say, what's the purpose of it? Why do I even care? And the answer is because sometimes they force you to use it. That's why I care. Because they could say something like, we know this interval is concave up and we know this critical value. And then you'd have to know, oh, it's concave up and this is the critical value, therefore it's a relative min. So if they only gave you information about the second derivative and a critical point, you would not know anything about the first derivative because you only knew the critical point. They didn't give you the first derivative. So you would have to use the second derivative test. Does that make sense? So they can, in a multiple choice question, they can manipulate whatever they want to give you. And so that's why we have to not completely ignore the second derivative test, because they might do that to us. Okay. All right, so we already know our min and max are good. Let's go ahead and find the stuff that we can from the second derivative test. So we know the point of inflection is at what? X equals -1/2, and we do know there is a point of inflection because this really did switch signs from positive to negative. Okay. We know that the graph is concave up on what interval? -3, -1/2. We know the graph is concave down on what interval? -1/2 to 3. All right, there's all our information. We're good. Makes sense? And then sometimes they'll include, in these types of tables, they'll include g of x, because where g of x equals 0, you're going to have your x-intercepts. And so that's important too, if it says where g of x equals 0, those are your x-intercepts, and that gives you something to graph. So, all right. I think that kind of sums up, that's a good summary of some of the stuff that was in that. And then, so here on 4, they did the exact same thing. They just put the two tables into one to mess with your brain a little bit. But you can do the same thing where you can split it up and make 2 sign charts out of it, which is what I would do so it doesn't hurt your brain quite so much. In 5, they did the same thing. They gave you a table, but they just did it in a slightly different form, mess with your brain again. So again, just turn it into a sign chart like we've done, because it'll be easier for you to interpret when it looks the way we've had it look. Okay, I'm going to go ahead and hand out the Larson pages. It kind of looks like I wanted you to do those first, which is why I had them written down first. So maybe start with that. Sound good? Yes.
Oh, I couldn't figure out 11. Hold gonna have to